right. Welcome back. We've had kind of a crazy week. Friday was pretty messy, so I just said let's do remote class anyway. Then Monday ended up being even messier, but we're back after a nice week-long hiatus. Yeah, Wednesday to Wednesday. Yeah, it's been 7 days since we've been here. So thanks for coming back. We're still dynamics, still applied mechanics 2. Was anyone having issues with like project 1? Because Friday the plan was meet up and kind of wrap that up. Did anyone that came today still have issues with it? No? No one wants to admit. It's like, no. That's okay. All right, so and I'm not pointing this out in anyone here in particular, because it sounds, at least from the no response, no news is good news. It sounds like it went smoothly. You communicated with your project members, with your group members, and then submitted like each of your free body diagrams to say these are the things that we thought of for project 1, like our proposal for module 5. But when you're trying to like communicate as a group, or even communicate about a group project, if you send me an email and it's just, hey, I can't find my group, or like my group's not responding to me, I don't know who your group is. I don't know what's going on. I don't even know what project you're working on. So some professional etiquette for emails. If you're sending an email, include everybody in your group. And again, maybe you already do this, so I'm not saying that anyone here is at fault. It's just I had a dozen emails over the weekend that all had different slices of information. Some of them I wasn't even sure if they're in this class or some other class. But so the first, very clear, like what task you want me to do. Like, do you need help? Do you need time? And then include everybody that is connected with the task. Just a little bit of professional advice. Sound good? So task and communicate. Keep everyone involved and make the task very clear. What needs to happen next? Cool? Otherwise, like, I don't know. Sometimes it's just like a whole bunch of personal information and I'm like, okay, I guess it's just for my information, and then, I'm not sure what to do with that. But we'll get there. That's what college is for, is like trying to figure this stuff out. So try it, include people. And so I guess some personal advice. This one's just like from years of dealing with other professionals. Like the reasons that things are late or the reasons that you can't do a task, nobody needs to know and nobody is worried about. The only things that they care about is what help do you need and when will it get done. And if you're communicating that clearly and regularly, then all sorts of other stuff can happen in your life. And you can include people that you feel comfortable including in those conversations, but you don't have to. Like, it's a professional work environment. You can just be like, shit came up and I'm not gonna do it today. And you know what? Shit comes up all the time, and that's okay. You can just say, well, I mean, I wouldn't use shit in your emails, but here's what's happening. I'm gonna get this done tomorrow. These are my group members, and this is what I need to do. No responses. Everyone's either staring at me like, you know this already, or like I'm speaking Latin of like, what is he talking about? What is an etiquette? Some kind of knife? Like niceness, professional niceness. Anyway, that was my little spiel for today. Now it's on YouTube, like recording. One other thing that was coming up for today as far as like stuff is we can get started on case problem 2. And there's also like the reading, or like the learning coach quiz 2. Those are the two things. So quiz 2 is due today. There are no late penalties for this class. So if something's late, that's okay. If it's going to be days late, then put a note into the submission and saying like, hey, this will be 2 days late. I'm working on it. And if you need help, let us know how you're getting help. Are you coming to class, you have questions, or you have someone that you're getting some help from. But either way, again, it's okay, but just let us know what's your new deadline and what help you need. More blank stares. We're good? Signs of life? Yeah, all right, some signs of life. All right, cool. I don't mean to, I know this is a lecture, but I'm not trying to like lecture you of like, this is the way the world works. I'm just like, this helps me work the world. Help me, help you, let's help each other. That's the goal here in our learning environment. But I know it is a lecture, so thanks for bearing with me. So let's do something fun. Do you know what this is? Yeah.
A jack.
A jack? Yeah. What do you use jacks for?
To lift up cars.
You could lift a car. Yeah. Why do you use like a jack like this? Couldn't we use like a lever? And just like,
A lever you have to like hold in place with something else, but the jack just like holds itself in place.
holds itself, yeah.
It's a lot more compact for the mechanical advantage.
A lot smaller mechanical advantage. Oh, okay. So lever, how big of a lever arm would we need? Let's say we're holding up 500 pounds, a quarter of a car. How big of a lever do we need? Yeah.
Depends on how much force you want to apply to your lift it.
Come on, how much force do you want to apply then? What's your rough estimate? How much force can a person apply? I know it depends. I know it does depend. And I know that's a great answer. It does depend. Yeah. They could use their body weight. So you could have someone like one person stand on the lever, the other person work on the car. I hope you trust that person.
We actually need it to be a small enough amount of force that it can't be overcome, that it can't overcome friction, otherwise the collar is just going to fall as soon as we let go of it.
Oh,
So-
in this case?
Well, if we have like a lever, right? and we're
Oh,
lifting
yeah.
up the car, we actually need the lever. We need to apply such little force that it sticks in place.
Oh, that
Or
it
we need to have
sticks?
a locking mechanism.
Or some kind of locking. Yeah, like maybe we have like a pin or something.
But it's actually the locking mechanism that's going to be the limiting factor as to how much weight we can use.
Yeah, but we could use like a big old steel bolt and lock it in place. So how much people weigh? I weigh like 190 pounds. So 190 compared to 500. How big of a, what's the lever arm difference to lift this thing? Call it 200 pounds versus 500 pounds. Right, so we have our lever. £200, 500 pound. When are those equal? Yeah.
You need the longer lever to 2.5 times the shorter lever.
2.5, something like that. 2.5. Yeah, like 2.5, something like that. So if we have a 1 meter lever arm, then we need an extra 2.5 meters. So now we're talking 3.5 meters of lever that you have to jam into your car, or like you have to carry it on top of your car. So we can get much, as was brought up, we can make a much more compact lever with a little car jack system, which is kind of nice. And there's actually 2 different places where we're getting some mechanical advantage, and we'll look at those as we're kind of investigating this project, this like case problem. Sound good? And should we copy this over so we have like, actually, let's just, I don't like screenshots, but I think it makes sense here. Okay, so we're using a car jack. First, we need a kinematic description of motion. We should probably zoom in. So connecting angles, collar motion, lift height, like all that kind of stuff. We need to relate like what is the load in our screw. So we're turning a screw to change how high the car is being lifted. So how does the screw motion, or what is the load in our screw? Kind of that part. Then the next part is like kinetic connection between thread pitch, like how many threads, maybe per inch or per millimeter, like what thread we choose, and then also like our mechanical advantage. And then we'll have to do, in order to kind of wrap this up, we need some research on like what a human can actually do. So with a lever, we kind of know. If you stand on the lever, that's max load that you can apply, because you can't put your foot on something and apply more than your own weight, otherwise you lift yourself and not the object. In this case, it's a little different, because now we can use like hand crank or something, so it'll be a little different than that. What do we think so far? You already know the answer. The answer. 42. It's always 42. What's the difference between our kinematic description and kinetic description? That's a big part of this class, and it's like one of the first things we started talking about. So here we need both kinematic and kinetic. What is our kinematic description telling us? Yeah.
It's gonna be like how the different parts of it interact with each other.
But does kinetic not tell us how they interact?
Kinetic is more of the motion, and the kinematics is more of the geometry of motion.
Kinematics is geometry of motion. Okay. Yep.
The kinematics are more about like position and stuff, so it's like meters and time.
Okay.
Kinetic is more like energy.
Kinetic could be energy. Yeah, it could be like how much energy we're putting in versus energy we're getting out, something like that. Yeah, so we can think of it in terms of like energy. Kinetic could also be like the force balance on this thing, like what force is necessary in order to create this object. But we touched on it kind of twice. Like kinematic is that geometry of motion. So when one part moves, what do the rest of the parts do? Do they all have to move with it, or are there certain parts that can move independently of each other? So that's kind of our first step. This is, so far, the stuff that we've looked at, all the kinematics was pretty straightforward. Stuff was moving in a straight line. We didn't really need to think about constraints and those kind of things. Now some stuff is rotating, some stuff is moving forward. This is where we have to start thinking a little more deeply about like what is the geometry of motion? How do we define it? And what are we doing there? So that's why I say we should start there. So what do we think? What is the geometry of motion here? Like what are some things that we could start with to describe the geometry of this motion? Take it like, oh yeah, if you have something, yeah, go for it.
Like it goes up and down.
Yep, so it's definitely going up and down. So let's say we have that thing, let's call it our support, or no, it's not a support. What's the thing called that actually touches the car? What would that be called? Strut? I don't know. No, the strut is in the car.
A little pad.
A pad? We could call it a pad. I like that. So let's say pad moves up. What happens to the rest of this thing? It's got to get smaller. Yeah, so angles have to decrease. Those two thetas kind of decrease. Cool. So our arms get closer, farther. All right, so take a minute. And you don't have to know the answer, but I just want to know where you're starting from here, like what you're thinking about in terms of like, how do we describe this motion? So one thing we kind of know here is that this, and this one I do give it a name, I think. Screw turns, collar. This collar, let's say the collar is moving at some constant rate, because that one we can control. We can like run this thing, move it at a constant rate. Let's say that's moving at a certain speed. What is the rest of the system doing? How do I connect that motion, that V, to upward motion? So is it a function of that collar? That moving thing? What do you think? How do you connect those? What do you think so far?
I mean, I'm thinking if the jack starts from the floor,
Yeah.
and you start turning, it'll start like to like spring up like this, and then
Okay.
eventually reach like straight vertical.
Yeah. Okay.
So I'm trying to like think about that in terms
So
of
the two extremes,
Yeah.
kind of like 90 degrees and 0, or yeah.
Yeah, I'm trying to think about that.
90. Okay. Yeah. What was your starting? Yeah. Okay. Yeah, like the number of threads will tell you that for every turn it'll move so many inches, right? Okay. Yeah, that's true. Yeah, so we know how like threads connect to collar motion, so we can connect that one. What do you think so far?
about these old days before, because remember you told me a year ago. Yeah, you can.
Any initial thoughts on where we can get started? Or start simplifying the problem? Because it's a lot to unpack, right? It's just like moving parts. Yeah.
We can do like some equation with like the initial height of the pad, and then like do one rotation and then thread rotation and see the difference and kind of form an equation from that to the end.
Okay. So and your thought was kind of like this threads per inch. Threads per inch is like the distance that it moves per rotation. So if it's one thread for every inch, then every time we rotate one time we move 1 inch.
Yeah, whatever the
Yeah, I mean,
Well, that's-
that's pretty high, but you could have like a massive bolt that has 1 inch threads on it. Probably not in the back of your car, but we can do whatever we want with the engineers. Oh, we can't see that. Yeah, so at least, and this is a great like kinematic, again, this is like describing just the geometry. We had some talk about like, will knowing the forces on this thing tell us the motion of this? And I'm trying to think of, like, if your speedometer is in your car, that is a kinematic description. It's telling you how fast you're going. If you know how fast you're going, do you know how much gas you're burning? No. I mean, you know you're moving 20 miles an hour. Sorry. Yeah.
Could you figure out how much gas you're burning based on your coefficient of drag and therefore how much horsepower you're putting out and therefore how much energy you're using?
So if we have some kind of kinetic equation that relates speed to like forces, then we can calculate like how much gas it takes. We can figure out like how much energy we're using. We know that our engine is only like 28% efficient, like thermal efficiency. So then we could kind of multiply that and get a number that way. But in terms of like, with just a value of speed, it doesn't tell us what forces are being applied to create that motion. It's just saying like, this is it. This is your, same with like GPS. GPS tells you where you are. It doesn't tell you that you're like, I don't know, James Bond hanging from the side of a satellite, like something. I'm thinking like GoldenEye. It's like that giant satellite dish at the end of the movie. Yeah, so the only, I guess, main thing there is kind of separating out, this is a good skill to have, especially for dynamics, is separating out what is kinetic information, what is geometry information. And geometries are kinematic information. Cool. Anybody see anything that could simplify the problem? Like could we split it? Solve for one side, and then just say the other side is going to be the same as this side? What do we lose by saying there's mirror symmetry? Do we lose anything?
Does is this side stationary? Like the left side, since the, like, angular, like, thread is only, the collar's only on one side?
Yeah, we only have like the one collar moving, right? I want to say that I do support the mirror symmetry, but I just wanted to know like what you're thinking here. So in terms of, we can say like this is our mirror line. But the question came up of like, if this is, let's call this distance D, will this also be a distance D? Like that's the mirror, at least when I'm looking at that and trying to figure that out. And would that always be the case? Yeah.
Only if we assume that our center screw doesn't flex.
Yeah. So hopefully we're choosing a screw that's not like buckling. Well, here it's under mostly tension, right? But it's not stretching or flexing, like. And so we do have some mirror symmetry, even though we're only driving one side of it. We can still use like some mirror symmetry here. Cool. So I'm gonna make it So I'm taking a simple drawing and making it even simpler. Like, now I have two moving parts. At least the things that I care, like things that I'm kind of looking at. How does that look? Is it still the same diagram? Are we still solving the same problem? Some people are kind of staring at it like they're not sure. It's too simple. Yeah.
I'm just not sure like how you like if you go back to like the split section, did you draw like a wall at the pad, or is that just like loose?
So I'm scrolling back down to my diagram. We're slow today. The wall there that I drew at part B, at hinge B. That one is a sliding constraint that it can move up and down, but it can't move left and right.
Okay, yeah, that's fine.
Okay, all right, yeah. Then we have L and L. So VA is some set value. Like if I'm moving it 5 millimeters per second, how fast does VB move up? Do we know? It's not immediately obvious. It's not like you should just know it. There's not an equation to look up.
For VA, are we talking about the linear velocity?
Yeah, so a linear, like it's moving, technically it's moving to the left and up because it's because A has to follow a circle, so it has to move in an arc. Let me see if I can catch this up here. So it's moving to the left, but like initially it's moving just up and to the left, something like that. We can say like roughly kind of constantly moving that way, because our threads are going to drive it that way at a certain speed.
If we assume like some kind of like angular velocity, say like I'm spinning the bolt at this many rotations,
Okay,
can
yep.
we go like from there to threads per inch, and then like basically use that as some kind of like conversion factor or something, and then we could find VA?
Yeah, I mean, if we, so part of this is a goal of, where is it? Is we want to figure out what the pitch should be, like how many threads per inch we need. If someone said like, hey, it's 10 threads per inch and it's rotating at whatever, 3 rotations per second, then we could turn that directly into VB is moving this speed. And we could start there, like how we did with the friction in the first case problem. We could just say like, these are the threads per inch, and I'm gonna solve for it. And if it turns out I need 3,000 pounds to move the thing, then we'll say, all right, well, let's increase threads pitch or decrease speed, something like that. Yeah.
So, can you scroll back down?
Yeah.
The two betas that are show up, those are equal because the lengths are equal. Like for both,
Ooh,
so if you
okay.
just figure out the other angles, those are the same.
Okay.
You can do like whatever arc, whatever finds that length there.
Define that length.
Yeah. and then
Okay.
the difference.
Yeah, so we could figure out like how high this thing is. The height of our jack based on the angle. Yeah.
I think you could further simplify this and just split it in half to figure out what the rate of change in height is of the lower arm, and then double it because it'll be the same, because they're both L, and then that'll be the rate of change of the height in total.
2 times L times, what do we think? What's the factor that we need for that one? I think you're right. Like, if the thing is 0 degrees, it's going to be 2L tall. But if it's at 90 degrees, if it's flat on the ground, then it's down at 2L times 0. So something, yeah,
Cosine theta.
like a cosine theta. Take that inner part. I like that. So here, kind of what we're circling around is this idea of how many degrees of freedom and how many constraints are on this system. So here, if theta changes, everything has to change. Or if we say that A is moving to the left, everything else then theta has to be some function of that, how it's moving. So we only have 1 degree of freedom. If we know that one thing, we can calculate the rest of the stuff. It might not be easy, like we have to do math to get it, but somehow it's all connected in motion. Cool. So we could say H is 2L cosine theta. What about like this distance? What do we call that here? D? Do we know how big that distance is?
Could we not just do like L sine theta?
L sine theta? That's what it looks like, right? Like we're using some trig to figure out how this motion is all confined. This was awesome. Within like a few minutes, you figured out what the constraints on the motion are. So now everything is a function of theta, right? Like, so that could be like our one coordinate, that if I know the angle, I know everything about this system. So we have constraints, we know kind of how they're changing. I'm putting some vectors in here. All right, we know how to describe like that height. We know how to describe that position of that second hinge. And I started labeling things just because I find it easier to have labels for my hinges as they're moving around. If you want different labels, you can label it your way. I like OAB, origin, A, B. B moves up and down, A kind of swings around in the circle. What is the position, what's position of A, what's position of B in terms of like a coordinate? So first we need like some coordinate system, and then we can figure out what the derivative is in that coordinate system. So what are those values? Like how do we get started with that? Yeah.
Well, if you derive D, you can get VA, I believe. So VA would be equal to L cosine theta. I don't know if that's right.
Does that sound right? L cosine theta?
Sorry, what was, R and what's the
Oh.
line over on the previous one?
Oh, when I put a line over something, that I'm just trying to draw a vector.
Okay.
Yeah, that it's got to have a magnitude and a direction. That's what the line means. In textbooks, usually it's bold to say it's like some kind of vector. I can't draw in bold. At least it doesn't look very good. So instead, I put a line over it.
And R was?
And then R is like a position. V is a velocity.
Okay, thank you.
Yep.
I just wanted to.
No, yeah. Thanks for clarifying.
So then if VA is equal to L cosine theta and H is 2 L cosine theta, would H just be 2 VA?
H is 2 VA. Something like that. How do we think? What do we feel about that?
I mean, that checks out, I guess.
Math checks out. Yeah. Can't argue with math. Give it a shot. See what you come up with. So, here's our question. H, or what is it? H is 2 VA? Is that what you said?
Yeah.
So the height is 2 times VA? The height equals 2 times VA? That one, the units don't make sense, but it's a question, and math can help us. So we can figure this out. Does the height equal 2 VA? I think I like the idea, somehow there's got to be this doubling, right? Something's got to double. Because if we move this one in 1 millimeter, we're probably moving up 2 millimeters times something, maybe some other function in there, but. Anything? Which do we? Okay. Yeah. Yeah, is that derivative? Is that one good so far? L cosine theta is the speed of d, or speed of A.
So that's something angular, because if we derive with respect to t, then it's not that.
Okay. Yeah, so far the units don't work out right, because we still have a.
If you do
Meter
d over,
times-
if you do d theta, then that makes sense.
Okay.
But this is time theta.
Okay. All right, so we gotta rearrange this a little bit, right? Chain rule. Chain rule. I warned you, I'd be yelling it out randomly. Does that help? Chain rule. Chain rule. Like that? Chain rule? How does that look? Copacetic? Usually, if you're taking derivatives of like motion and angular motion, you end up with like some kind of theta dot term in there. So, and especially anytime something's like rotating on a hinge, there's almost always some kind of theta dot dependency of it. Oh, and you can only see a part of this, so let me scroll down a little. It's just my beautiful face blocking all of our hard work. Theta dot cosine theta. Something like that.
It could mean anything. Charge.
We can do so far. We have like a can we say anything about H and VA? So how much velocity of that screw it.
I mean, just based on the logic that screws everything. It's a small, fast machine.
I think it's got that it's got to move faster for a given height.
This moves its been. It'll be faster than power. It's the faster.
Okay. Yeah, in this case, so I guess you're kind of thinking of like if that support is moving at a constant speed, how fast is this thing keep up with it? And I approached it in the inverse. If this is moving at constant speed, how fast is this moving? But they're both similar questions. Right? Like if we get into one, the other one's kind of inverse. Out of time. Time flies. You're having fun. Cool. This was a great start. So this, I just wanted to say, I don't think we can say that height is directly connected to velocity, but I do think there is a connection between like the two velocities. Like if one's moving one speed, the other one's going to move kind of 2 times something times the other speed. So there is something. We're getting close of like somehow there's a proportion between VA and 2V or 2VA and VB. Cool. All right,
Isn't
we'll
that
pick
like
up.
alpha?
Oh, proportion to. Yeah. It's a fish. Proportional fish.